Hi everyone, we are continuing our list of reactions for ketones and aldehydes, and we are up to acetal hydrolysis, and oh, this is new. We are going to learn about the concept of protection groups that we can use during a synthesis. Now, as a reminder, in video 0 to E to 0, we did the formation of acetal or acetal formation. Hydrolysis is the opposite. Hydrolysis is we're going to take an acetal and we're going to break it up into the starting material that made that acetal. So it would be nice to look at how to make an acetal or remind ourselves how to make an acetal, because when we take an existing acetal and do hydrolysis, what is that? Lyse means to cut, and hydro, we're going to use water to cut up the molecule so it looks like it's starting material again. For instance, if I have, and this is review, if I have this ketone and I use ethanol in excess and we use H2SO4 as the acid catalyst, what we get is the acetal, and remember, we're going to put the two alkoxy groups on the same carbon. So there's one, there's two. Okay. The thing is, now for this reaction, acetal hydrolysis, if we take this acetal and we hydrolyze it, hopefully we get back the ketone and the alcohol. Okay, so this is going to be reaction, we are up to reaction G. Yep, reaction G. And we'll call this acetal hydrolysis. Remember when I did the mechanism for acetal formation, I was using a bunch of equilibrium arrows because this is reversible. And how do we make it reversible? We use Le Chatelier's principle, and we add a lot of the products to drive the reaction back to the starting material. What is the product, though, that I want to add? You notice that, or maybe not, remember when we're keeping track of the oxygens? These two oxygens are from the alcohols. We say that the alkoxy groups are from alcohols. So where did this oxygen go? In the mechanism, it eventually left us water. So the thinking is, if we could add some acid and add a lot of water, then we could actually go backwards to reform the alcohol and the ketone. And that's what we're going to do for acetal hydrolysis. We're going to take an existing acetal, and yeah, why don't we just take the one that we made in this reaction. I flipped it by accident, but it's the same acetal. Okay, and we're going to add water, hydrolysis or hydrolysis. We're going to cut with water, and this is going to be acid catalyzed again. But now instead of a lot of alcohol, we're going to have a lot of water. And let's see if we could get back to the starting material. Now, to do this the quick and dirty way, we're going to cut. And you're going to cut in between the carbon of interest, the dot, right? That was the carbon of the carbonyl. You could put a dot right here as well. Okay, we're going to follow the dot. And you're going to cut right here. Because weren't those the two bonds that were made when you made the acetal? And then you're going to separate them. Separate their pieces. And we have this with the dot, okay? So literally I'm cutting and I'm separating. Okay, give some space. And we're adding water, H2O. H, H, O. Okay, so don't forget to remake your carbonyl group. Now, yes, your two alcohols are identical. I typically accept this as an answer, even though these two are identical. I'm not going to worry about that you only make two organic products, right? These two. It just shows me that I know what you're doing. You're just cutting and you're separating and you're adding your water. Okay, let's go through a couple of other examples using this trick, all right? And I think I am going to show you the mechanism. Okay, so let's do one more example. Now this example is a little bit trickier because one of the alkoxy groups is part of a ring. But do you realize that this also is an acetal? It's an acetal because you have this carbon, okay, right there, that's connected to two OR groups. In this case, we technically form two products, the ketone and this alcohol, okay? But we form two servings of this alcohol, right? But if we're just looking at the identity of the products, two products, what about for this? Okay, we're going to do our cuts, okay, and we're going to separate again. Separate the molecule apart. Again, hydrolysis is cutting with water. You do need to show that water molecule. And let's see, how do we spread this out? Well, you notice that this oxygen is still connected to the ring, or the part of the ring down here, and we're going to swing it out like this. We have this dot, okay, but literally, right, if you had this in 3 dimensions in your hand and you just cut that bond, wouldn't this top piece fly off? So that piece is flying off and it's right there. Add water. H2O. Okay, almost messed up there. Double check your carbon count. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this alcohol, 1, 2, 3, 4. 1, 2, 3, 4. The thing is, now, the starting material, if we were making this acetal, had the carbonyl group and one of the hydroxyl groups in the same molecule. And that's why we ended up with a molecule that had both the hydroxyl and the carbonyl. Okay, so that's one of the trickier versions. I did say that I was going to do the mechanism. I am hesitating because it's long and messy, and honestly, it's the backwards of acetal formation. But why don't we do this? Why don't we do the mechanism? And let me pick a simple, so I'm not drawing all day, a simple acetal. OCH3, OCH3. Okay. Can you visualize what our products are going to be? It's going to be 2 methanols, and we're going to have, if you cover up the top part, you're going to have a carbonyl group at that dot. We have acetone. Now, if you're doing this for the first time, or even if you're doing this for the 10th time, all right, and it's still kind of unsure, you could always use, and I have our mechanism from acetal formation from the previous video, because acetal formation is the reverse of acetal hydrolysis. So now we're going to start here, and I'm just going to do a little cheating. I'll look at the last reaction here, which is the first reaction for our new mechanism. And what is the little bit of cheating? The cheating is in the 7th step, we deprotonated. The 7th step, we deprotonated. So in the first step, in the reverse direction, we are going to protonate. And I'm going to protonate. Oh, we're doing hydrolysis. So we do have H3O+. Okay. I am going to protonate. Now, a lot of times, the strategy to learning these mechanisms is if you could get through the first step, probably the hardest part is getting started. Okay. I don't know what's going to happen next, to tell you the truth. I don't know what the second step is. Let me draw the product of this first step, which I know is true, and see if I can figure out a way to get closer to the product. Okay, so this is a little bit of a risky move. We have this plus. Well, if I think about my target, and I'll just put it off to the side, the target is what? The target is this ketone plus 2 molecules of methanol. Okay, 2 molecules of methanol. Well, what that tells me is that I got to kick out these alkoxy groups from this dot. We're going to do it this way. We are going to, remember how we had this double bond in the acetal formation? That's how we're going to kick this out. And maybe I really should use equilibrium arrows. Let me revise this arrow. Okay. Okay. So now I'm building off of this molecule and asking what could I possibly do to get closer to my targets? Well, when I kick that methanol out, what do I have? I have this so far. Plus methanol. Great. We have already accomplished one alkoxy group becoming a alcohol. The thing is, this oxygen came from water. Okay, this oxygen came from water because the oxygens here are coming from alcohols. So that has to leave. Okay, but we have to replace it with an oxygen-containing molecule. We are well set up. Are we well set up? We are well set up to start to lose bonds to this oxygen here. And the first step in that task is to add water. If I was taking the exam, right, there's no way that I would do this just once, because as you can tell, I'm a little bit slow. I want to do this, if I feel like the professor's going to ask this problem, hydrolysis, mechanism of hydrolysis, I would do this a couple times. And we have this. Okay, I think we're getting closer. What do I have to kick out? I have to kick out this oxygen, but I want to keep this oxygen. So let me do a deprotonation. I'm just checking if I'm missing any molecules. Like over here, we created water. Okay. And then here, that's good. We created alcohol. We used water to get this. Okay. I think we're all caught up. We're going to do proton transfer because the goal is to keep this oxygen, but to get rid of this oxygen. So it comes off as methanol again. Well, for it to come off as methanol, we're going to have to protonate it. But I don't want to have two oxygens protonated in the same molecule. Let me get rid of this proton down here. Right, eventually, this oxygen has to be just oxygen. Right, this oxygen is this one over here with no hydrogens. All right. Feel like I'm flying by the seat of my pants, but this looks reasonable. Okay. And we also created acid, which is great because I do want to protonate this alkoxy group. All right, before we go on, make sure everything is good. Before we go on, do you remember how many steps it was to do acetal formation? The mechanism took 7 steps. From the previous video, to make this acetal way down here, I numbered the steps in pink, 7 steps. Okay? We expect to do this in 7 steps also, this hydrolysis. We're already up to 1, 2, 3, 4, and we're about to do number 5. Okay. Again, just keep track of the target. Let me circle the molecules that we've already made that satisfy this target. We already made that, but we need a second molecule of methanol, which is going to come from here. All right, let us protonate so this becomes a good leaving group. We created water again. Okay. All right, let me zoom out so we can definitely see the whole mechanism at the same time. Good. Remember how we kick out? We kick out using an internal lone pair. And there's my second methanol. HOCH3 plus. Do we have the ketone yet? Not quite. We have this oxygen, but see that hydrogen still is attached. And I'm just going to use water again to deprotonate. And what I'm hoping for, I don't know yet. I'm hoping that we have 7 steps. And it's the complete backwards of what we did in the last video for acetal formation. Okay, the acetone got upside down, but that's fine. And we have H3O+. It's a catalyst. Okay, 7 steps, right? 1, 2, 3, 4, 5, 6, 7. Who knows what your professor's going to ask? Are they going to ask the mechanism for the forward direction, the formation of an acetal, or are they going to ask for the backwards, the reverse, the hydrolysis of an acetal? You would want to practice both ways, just in case they ask one or the other. Good. The second half of this video is cyclic acetals as protecting groups. Okay. Let me show you that. It's a very interesting concept, and a lot of organic chemists, when they're making really complicated molecules, have to go through what's called a protecting group. A protecting group does what it says. It protects a functional group from reacting. And why would you want to do that? Because maybe you want to react one part of the molecule but not the other. But what if both parts are reactive? You want to protect the one that you don't want reacting. Okay. I'm going to give this a new letter. Let's call this H. All right, so reaction G was acetal hydrolysis. H would be, let's say, well, just call it cyclic acetal as a protecting group. Let me show you, oh man. Let me show you how to make the cyclic acetal and why we can use it, or how we can use it as a protecting group. So this is going to be interesting, because do you remember how to make an acetal? You make an acetal, let's make it a little more interesting. You make an acetal by reacting this carbonyl group with how many alcohols? 2 alcohols, right? Because we want to have 2 alkoxy groups. But how do we get it to be cyclic? Well, imagine if these 2 oxygens were connected even before you added it to the carbonyl group. So imagine if this carbon was connected to this carbon. What would that molecule look like? Well, a very popular way to protect or to make a cyclic acetal is to use this molecule here. Huh. Why is that going to work? Because we still have 2 hydroxyl groups, so we could still add 2 alkoxy groups to our carbonyl group, to our carbonyl carbon. So just go ahead and draw your carbon skeleton and draw or start drawing your acetal. Normally you would have 2 groups here, like maybe a methyl and an ethyl, or 2 ethyls. So, normally you would start drawing bonds away from each other, away from the 2 oxygens. But my 2 oxygens are already linked by 2 carbons, this carbon and this carbon. My 2 oxygens are already linked by 2 carbons, this carbon and this carbon. That is a cyclic acetal. Now, this is very effective because once you get the first alkoxy group on, the second OH is actually really close. It can't escape. It's connected. So it's actually more likely to close a ring than if you are reacting it with 2 separate alcohols. Okay. So this is called a cyclic acetal. And the idea here is that you could do any other reactions, all right? Okay. And then when you're done with all your reactions, you could do what's called a deprotection. So in pink, I'm going to label this as quote unquote protection. Protect that carbonyl or hide it. You could always get it back. How can you get it back? You do the hydrolysis reaction. Because see, we got back the carbonyl group by doing hydrolysis. Okay, I know it looks a little silly. I mean, we just made it. Why are we destroying it? Well, we're not using this yet in terms of synthesis. I'm just showing you what the strategy is. So what is hydrolysis? You cut, and then you add water. And I know, all we're doing is forming the starter material. Plus, we have this. Okay. Why is that useful, or how is it useful? It's useful because what if I have... Actually, before I tell you why it's useful, let me give you one statement that's going to help us use this as a protecting group. Okay. The statement is this. If you have an aldehyde ketone, right, a molecule with both aldehyde group and a ketone group, maybe something like this. There's my aldehyde at the end, and here's my ketone in the middle. If you have an aldehyde ketone, it is faster to protect the aldehyde. That has something to do with electronics, that this is more reactive, this is more partial positive, but also it has to deal with sterics because this is less crowded. And so what I'm saying is that you can selectively protect an aldehyde over a ketone if they're on the same molecule. Selectively protect. Okay. All right, so if we have our diol, I'll use hydrochloric acid in this case, you will be able to protect in pretty good yield the aldehyde over the ketone, and this will be close to 100% yield. Okay, that's where we're going to use, or that's why we can use this as a protecting group, because my task, for instance, can be how do I make this molecule here. If I start out with this aldehyde ketone, and let me choose another one like that. Okay. The way that I ask for synthesis is 3 arrows and a question mark. I'm not saying that the synthesis takes 3 reactions. I'm just saying that the synthesis takes more than 1 reaction. It could be 2, it could be up to 8 or 10. But I want to make this molecule here. Almost messed up. That and that. You may know how to make this part, okay? And so here's a guess, a proposal. What if I do this? What is that? That's the carbon anion, the alkynyl anion. Oh, I know what to do. I can just react it with this salt and then protonate that oxygen with acid in the second step. Okay, you're not going to mix these two together. You're going to do these separately. The thing is, that nucleophile will most likely attack this first, or you'll get a mixture. So you don't make this product in good yield. You can make some of it, but what's preventing it from reacting with the aldehyde? And there is a bad synthesis, because we get a mixture and we can't really control where that alkynyl ion attacks. So this is no good. This is not a good synthesis. Okay, because we get a mixture, a bad mixture, maybe even a 50-50 mixture. Heck, maybe an alkyne anion will attack both of these for one molecule and leave a molecule unreacted. We're going to use the concept of protecting groups, PG. I'm going to protect the aldehyde because I don't want it to react. And when I protect it, I am going to have a way to what's called deprotect it. Okay. How am I going to protect the aldehyde? I'm going to use that diol. Now, this is my favorite way to protect an aldehyde, but you could also use a diol that has 3 carbons in between. Okay, not a big deal. You'll have a 6-membered ring instead of a 5-membered ring. Okay, all right. So I said that this is selective, so we do get in pretty good yield this cyclic acetal. The point here is that now when I do this reaction, and I won't draw the charges, I'll make it a salt. When I do this reaction, the right side of the molecule is unreactive. You don't use carbon anions to attack that carbon. You only use them to attack, in this case, carbonyl groups. There was no reaction that we've ever learned where a nucleophile will attack this carbon. Okay? The only reaction that I know is we could hydrolyze this. So when we do this reaction, yeah, we do get this molecule. And let me draw it down here so there's more space. I have accomplished the fact that I got the alkyne onto that carbon, which I wanted to do for my target. Okay. And I did not react with the alkyne anion, the other right half of the molecule. That right half of the molecule. So we're close. We're going to do hydrolysis now. H2O, H2SO4. Sometimes people use heat for hydrolysis to make sure it all comes off. For me, it doesn't matter. Hydrolysis. You still have this alkyne alcohol on the left, and then we're doing hydrolysis. What is that? That's just cutting this apart. And we get back the aldehyde. Now you don't have to draw the diol. Okay, this is called actually ethylene diol. We got rid of it. So remember, with the synthesis, you're allowed to pick and choose what carries forward. The thing is, if you're making a mixture, like in this case, it is very inefficient and you'll have some points deducted. So where is the correct answer? The correct answer is here. Okay. This is an attempt, but I realized that it was a bad attempt because I'm getting a mixture. Because, again, that anion can attack either carbonyl. But here, the protection, you can protect an aldehyde over a ketone, and then you're off to the races. You can do whatever you want to the ketone without worrying about anything happening to the aldehyde, because you can always get it back when you do hydrolysis. Above here, I labeled protection, okay, to make the cyclic acetal. Where's the protection? The protection is here. And what do I call this? This is called deprotection. We reveal the aldehyde in the last step. Okay. Now there will be some strategies where you don't want to deprotect at the end. You may want to deprotect somewhere in the middle if you want to react the aldehyde eventually. But in this case, I wanted to keep it, so I kept the protecting group all the way until the very end, when I was done with the rest of the molecule. Okay. And again, there's your target. Later on in the course, we're going to see other types of protecting groups and other, hopefully other ways to use this type of protecting group, the cyclic acetal.